All right then. So, here we go. Review sesh. Okay. So, does anybody have any problems with that if I skip right to the second one and then we can do the first one also? But like I say, I think the first one, difficulty-wise, is maybe a little bit more like what you might expect to see on the exam on Friday. So, you guys want me to just read the answers and then we go over the ones you guys struggled with? You want me to do the whole thing? Just do the whole thing? Watch me go. All right, so here we go. So this is FRQ number 2. That rhymes. Why is my smartboard being dumb? There it goes. All right. Okay, so here we go. So here's what we know. We know that the mass of our object is 3 kilograms. We know it's moving along an x-axis in a region where its potential energy as a function of x is given by this. And it's actually not that complicated of a function here. So it's just 4x squared, where u is in joules, as x is in meters. It says when the object passes the point x equals negative 0.5, so at x equals negative 0.5 meters, we know that the velocity is 2 meters a second. All forces acting on the object are conservative. All right, so that statement right there is super important. What's that telling us?
You can do that there's no outside force acting on it other than gravity or elastic.
Okay, good. Well, I guess you could make the assumption that this is elastic just because it's of the form kx squared. 1/2 kx squared, I guess. All right, but there's something bigger. Something bigger. Yes, I agree with that. Molly, we got
the total energy.
There you go. Our total energy is going to be constant, right? Because if all the forces are conservative, that means there's no way we can have non-conservative forces doing work, right?
Yeah.
Follow? So remember, the only time your total energy will change is if you have a non-conservative force doing work. And we haven't gotten to that yet. That's actually what we're going to do when we come back from midterms. All right. So our total energy is constant. So what might be a good place to start, regardless of what the questions ask us? Calculate the total energy, right? Which, fortunately, is the first question. A says calculate the total mechanical energy, right? So, what are the 2 types of energy this thing's going to have?
Potential and kinetic.
Potential energy due to this, and kinetic energy because it's moving, right? So my total energy is going to be my u plus my k at 1 instant. Oh, and this should give me enough information to find that, right? So let's see. So my u at negative 0.5, if you plug negative 0.5 in here, you're going to get just 1 joule, right? Notice the negative squares out. Everybody cool with that?
Yep.
All right, and then we can find the kinetic energy at that same instant. It's going to be half of the mass times the velocity. Don't forget to square it. And that gives you what? Oops, 6 joules? Out of my way, recordy thing. Way back.
You know what was the saddest thing the other day? I was in the hallway and I saw some dude with the same coat as me and I said, "Hey, nice coat." And you know what he said to me?
Huh.
Nothing. He just kept walking.
That's rude.
Maybe you just didn't hear me.
I'm not a nice person, so when I'm nice to people, I expect them to be nice back.
Here's a worse thing. I was walking, this was when I was at U about, part of the reason I left. I was walking through the DIAG. Are you guys familiar with the DIAG at the University of Michigan? There was a group of University of Michigan students playing hacky sack. And I was in a happy mood, and I said to them, "Hey, who's winning?" And one of them said, "You are, asshole."
Damn.
I was
Insult.
I don't know.
Well, congratulations, you're
Yeah, it was really weird. A very strange response, right? From like,
Maybe he was losing and he's neutral.
I don't know what his deal was, but he was an angry Wolverine.
It was that time of the month for him.
Yeah. All right. So, is everybody good? So let's get back on the physics wagon. Are we all good with what I did here? So what? Yep, I'm recording. And yes, so yeah, that's.
Yikes.
So, Mr. Hacker potty mouth. Although I was quoting, to be fair. Okay. This time, right? Okay. I've been trying to be better about it. All right. So what's my total energy going to be, guys?
7 joules.
7 joules. Is everybody good with that?
Yes.
1 plus 6. All right. Very good. Okay. Part B. So here's what we know. We know our total energy is 7 joules. Part B says calculate the x-coordinate of any points at which the object has 0 kinetic energy. Well, look, you guys, if the kinetic energy is 0, then
Potential is 7.
the potential is 7, right? So we know that u is 4x squared. So 7 equals 4x squared, and solve for x. Divide both sides by 4, take the square root, and you get x equals positive or negative whatever root 7 over 2 is. All right? On the AP exam and on the midterm, you should convert that to a decimal. Don't just leave it in that form. Okay? They are really, really lax about sig digs, so do 1 or 2 decimals, and you should be in good shape. Cool? All right, everybody good with part B?
Yes.
All right, part C, calculate the magnitude of the velocity when x is 0.6. So this is part C. So part C says when x is 0.6, what's the velocity? So what should we do?
Oh, I got this.
What do you got?
Okay, so you put that into the potential energy equation,
So we're going to find u at 0.6.
and then you
So,
subtract that from 7.
yeah, so let's see, 0.6 squared is what, 0.36? Times 4 is 1.44. Everybody good?
You subtract that from 7, and then you find your velocity.
Okay, so is everybody good with this?
Yep.
All right, and then, yeah, we know our total energy. Our E mechanical has to be 7 joules, so subtract to get your kinetic energy. Turns out to be 5.56 joules. Think those add up?
Yes.
And now we can find the velocity, right? And the velocity turns out to be 1.9 meters a second. Incidentally, guys, this problem is like a real old FRQ. Like this was an actual FRQ from an AP test. So this one's, I think, on the easy side.
I actually like our midterm that part. Sort of.
Well, I mean, the whole thing is FRQ, right? Just not.
Wait, so how many questions are there?
I'm not done writing it yet, but it'll be reasonable.
If you say 8, I'm going to because there were 8.
Give us a range.
I mean, it's tough because there's always parts A and B, and you know what I mean? So it'll probably be, I don't know, 2 pages front and back.
Oh, that's,
Maybe 1 more page if I need, I don't know.
I got you.
So
And it
it'll
has
be all right.
enough space to like.
To work, yeah. So you'll be all right. Okay, everybody good? All right, part D. So this is the first one where like you actually need to do something other than just total energy is constant, right? So part D says calculate the magnitude of the acceleration of the object as it passes x equals 6 meters, or 0.6 meters. So at x equals 0.6 meters, the question wants to know what's the acceleration. All right? So when I first read this, my knee-jerk reaction was, oh, well, we just found velocity, so there should be some connection there, right?
Sorry.
I don't know that that gets you anywhere. All right? So what's the thing that's going to connect sort of this information about potential energy with acceleration? Sure, what do you got, Josh?
You know that you change it, use work or negative work, and then the derivative of the work will be a force, and then you just divide by mass.
Yeah, good. So both acceleration and work, or acceleration and energy, are related to force, right? So we need to find a way to come up with that force, right? So here is what we know. We know that the force, the amount of force exerted is equal to the derivative of the work done by that force with respect to x. That's the same as negative du dx. So that's negative derivative of 4x squared, right? So I think that gives us derivative of this. You bring the 2 down, so you get 8x, right? Negative 8x. Everybody good? So the math here is not too difficult, but it's just like applying, you know, concepts. All right, so now that we know this, we ought to be able to find our acceleration. So acceleration should be force over mass. So negative 8x over our mass, which was 3 kilograms. So you get negative 2.6x. And now you can plug in your value of x, right? 0.6. And it gives you 1.6 meters a second squared. Oh, it does say magnitude. You're right. So you don't need the negative. Thank you. Good call. Everybody good?
What was the final answer?
Well, and then, yeah, Josh is exactly right. Technically, because it asks for magnitude, you should omit the negative sign. If I remember right, and I'll make sure I do some more research on this before the actual test comes around, well, and obviously, if it says magnitude, then make it positive. I don't think they take points off for that, though, because I think they're more interested in how to solve it. So. All right, any problems up to there? Okay, the last part of this, you really had to do some thinking. So part E says, on the axes below, sketch graphs of the object's position, x, versus time, and kinetic energy, k, versus time. Assume that x equals 0 at t equals 0. The two graphs should cover the same time interval and use the same scale on horizontal axes. Okay? Hey, Mr. Hernandez. Thank you very much for doing that. I really appreciate it. You guys all know Mr. Hernandez? This is what he looks like. Thank you. Oh. You sure?
Yeah.
All right. Thank you. Okay, so we want to make two graphs here, right? So we want to make two graphs. So we want to make a graph of position versus time and a graph of kinetic energy versus time. Now, this is weird, and I remember the first time I read this problem, I struggled a little bit, because usually, when you're dealing with energy, you would want to graph kinetic energy versus position, right? Because work is force times, you know, change in position, right? Okay? So my natural inclination was I wanted this to be x, but then obviously you can't graph position versus position, because that would be silly. Right? Okay. So the only thing that it tells us is that x is 0 at time 0. Okay, so that's the only thing we know. All right? Now, here's the deal, though. So, how do we want to do this? So at that instant, let's do it this way. So at this instant, if x is 0, doesn't that mean u is also 0? Okay. Oh. Well, if u is 0, then we ought to know what kinetic energy is, right? What should my kinetic energy be? It should be 7, right? Oh, cool. So 7. Because our mechanical energy is 7, right? Does that make sense?
Yeah.
Okay. So that means it's got to have some velocity. It's got to have a pretty big velocity, right? Now, we don't necessarily know what direction it's moving in. Okay. I don't think there's any way that we would know. We just know that it's got to have a kinetic energy of 7. So that means it's got to be moving in a positive direction. All right. So my position graph needs to... Did I just say that right? I think I just said something that didn't make sense, didn't I? Patrick, you're making a squinchy face. We don't know that it's moving in a positive direction. Let's assume that it's moving in a positive direction, I think is what I was trying to say. So that means that my graph, my position time graph, needs to slope uphill. Everybody good up to there?
Wait, so we just were like, it's going to go forward.
Wait, what?
Yeah, absolutely. Sorry?
Because it has a positive velocity.
So what's the equation for kinetic energy? 1/2 mv squared, right? So the fact that the kinetic energy is positive doesn't necessarily tell you that the velocity is positive. Okay? Make sense? All right. So, as my position increases, doesn't that mean that my potential energy is going to increase? Oh, and as my potential energy increases, the kinetic energy has to decrease, right? So my graph has to start something like that. Okay? Hello.
Hello.
Everybody good? All right. Now, the other thing that I know is that, well, I guess even really, maybe I should be looking at this. My acceleration is this, negative, right? So my velocity's got to be decreasing, right? Does that make sense? So how do I, on this graph, how do I indicate decreasing velocity, you guys? On a position time graph. To indicate decreasing velocity, I need my slope to get less and less, right?
Yeah.
Good? Yes. All right, now, tell me something important about this point. Well, you jumped a couple steps. Something very simple but important about this point. The velocity is 0, right? So what does my kinetic energy have to be at that point? 0. So my kinetic energy there has got to be 0. Good? Now, if my position's decreasing, that means my potential energy is going to decrease. So what does my kinetic energy have to do now? It's got to increase again, right? So I'm looking at something like this. Notice your kinetic energy is never negative. Because kinetic energy is never negative, right? It can't be. It's 1/2 mv squared. Mass is never negative. V squared is never negative. Kinetic energy is never negative. Cool? All right. So let's see. So now our kinetic energy is decreasing. It's eventually, I'm sorry, our potential energy is decreasing, right? So at that point, your kinetic energy ought to be back up to 7, right? Cool? So now what's going to happen? How do we finish? Well, so is everybody good up to there?
Why did it go back up to 7?
As my position decreases, remember, U is 1/2 kx squared, right? Oh, sorry, I should do ke here. So as my position decreases, so does my potential energy, right?
Oh, because they're directly proportional.
Did I explain that right?
Yeah.
As position
Let's see.
increases.
So yeah, so here my position is decreasing. Good, right? Because remember, our velocity was decreasing, right? And eventually the position starts decreasing as well here, right? So if the position is decreasing, my potential energy is decreasing. If potential energy is decreasing, then kinetic energy must be increasing. So that's why this had to come back up again. Secondly, it can't go below 0. It's the only thing it could have done is come back up, right? Follow?
Yeah.
Well, I would say it's 0, but
I'm sorry? All right, so now what's happening is it's moving in a negative direction relatively quickly, right? But now my position's negative. So remember, our acceleration is negative, what was it, 2.6x? Something like that? So now my acceleration needs to switch to positive, right? So my velocity needs to get less negative, right?
yeah.
So you're going to get this. And so this point corresponds to this point. What's my velocity going to be here, you guys?
0.
Right here, the velocity is 0. That means my kinetic energy needs to be 0. Cool?
Wait a minute.
No, not really.
All right, so let's kind of break this down and see if this makes sense, because a lot of you just went, wait a minute, what's going on? All right, so look, at the very beginning, you're going quickly, right? High kinetic energy, right? As you slow down, your kinetic energy gets less and less. This is the point where you stop, right? Then this graph gets steeper and steeper and steeper. That means you're going faster and faster, right? As you go faster and faster, that corresponds to an increase in kinetic energy, right? Okay? Then, once you pass this point, you start slowing down again, right? So that's a decrease in kinetic energy. This question right here is harder than anything that's on the midterm. And it's a thing that, like, long term, within the next, whatever it is, 100 days that we've got, I think it's 109, I'm guessing. There's a countdown on my website. We need to figure those out. When did you start tasks? Sorry, Carlos?
Your acceleration change, because is the velocity supposed to keep going negative and negative and negative?
The acceleration is changing, and here's how I know that.
Oh, right.
There's an inflection point right there, right?
It's 2x. That's why I was confused. It's x. I see now.
Good?
Yeah.
All right. Are we good, you guys?
Yeah.
All right. I would say don't get too bogged down with that one, except to understand that the steepest parts of this graph should correspond to the highest kinetic energies. Okay? Right? Because steeper means faster, means more kinetic energy. I would say make sure you understand that your kinetic energy can never be negative. All right? And I guess the fact, does it make sense that this graph is symmetric because of the x squared here?
Yeah.
Okay. All right, so any questions on that? All right.
It's oscillating all the time.
Yeah, so this is basically, you guys, this is basically, I had it set up last year and I haven't set it up again this year. You guys remember last year I had a track set up with a cart attached with 2 springs?
Yeah.
You can pull it one way and go womp, 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 back and forth. You guys know what I'm talking about?
I know what you're talking about.
One person does.
I know.
Okay, all right. So that's basically what this is. Okay, everybody good? All right, should we go back and get number 1? Okay, number 1. All right, I really like this problem, and I think because of the absolute lack of numbers, probably a little tough for the midterm. But again, it's something we need to get there. All right. So here was, I think, the most confusing thing about FRQ number 1 on this review. The coordinate system is not the way that I probably would have set it up. So you've got this ramp with a motion sensor on it. And the coordinate system is set up this way. Here's your y-axis. That's what I would usually call the perpendicular axis. And there's your x-axis. All right? So here's what we know. The block has a mass, m. Hello? It's projected up from the bottom of an inclined ramp with an initial velocity of magnitude v0. The ramp has negligible friction. It makes an angle theta with the horizontal. A motion sensor aimed down the ramp is mounted at the top of the incline so that, and this is important, the positive direction is down the ramp. So that means this is positive position. All right? The block starts a distance d from the motion sensor. So this distance here is d. Okay? The block slides partway up the ramp, stops before reaching the sensor, and then slides back down. All right? So, what's my starting position, you guys?
D.
D, do we agree with that? Starting position is D?
Yeah.
Cool. What's my starting velocity? What's my initial velocity? V0, sorta.
Negative.
Negative.
Oh, because it's going up.
Because it's going up the hill. And we have determined that down the hill is a positive direction.
Yes.
All right? Hey, guys.
Hey, Joe.
I recorded we're doing number 1. We already did number 2. I recorded it.
There's some swearing in the language.
There is, yeah.
Your parents need to sign
All right. So, does everybody understand why we need to make that initial velocity negative v naught? Yeah.
So if we didn't make that way negative, it would have been fine.
Nope. The problem tells you
Okay.
that you have to set it up in such a way that down the ramp is positive. Good?
Yeah.
All right. So, with that in mind, let's see. Part A says, consider the motion of the block at some time t after it's been projected up the ramp. So our time begins at this instant, right? Okay. Express your answers in terms of m, d, v naught, t, and theta. So part Roman numeral 1 says, find the acceleration. Let's see, so what do we got? A, Roman numeral I. This wants to know the acceleration at time t. So you guys help me out. Thoughts about how to find this acceleration? That would work if we had an equation for the velocity. There's an easier way to do it though. Somebody got an idea?
Net force, which is just going to be mg sine theta.
Yeah, you guys agree? Aren't the forces on this thing going to be constant?
Yeah.
Ooh, yep.
So we should probably make a free body diagram, right? So let's do that real quick. I'm going to do it over here because I got a little bit of room. So what forces are acting on it? Well, let's see. There's the force of gravity, which automatically I'm going to split up into components. So there's my parallel, or my perpendicular component, which is mg cosine theta. There's a normal force, which is exactly big enough to cancel out that perpendicular bit. And there's a parallel bit, which is mg sine theta, right? All right, keeping track of my signs, I guess technically this should be negative, and my normal force is positive. This business here, my FG parallel, positive or negative?
Positive.
Positive, because we decided down the ramp was a positive direction. Or well, we didn't decide, the problem decided for us, right? Okay? So, what's my net force? Mg sine theta, right? So we can do now net force equals net force, right? So let's see, mass times acceleration equals mg sine theta. The m's cancel. There's your answer. Acceleration at any time t is just g sine theta. And then I would take a minute and convince yourself, positive or negative, positive, so we're good. Remember, g is understood to be positive 9.8, not negative 9.8. Cool? Right, so that is Roman numero 1.
So leave it at that because the unidirections of expression in terms of. So just leave that, even though we have we aren't given theta.
It says to answer in terms of m d v naught t theta.
Okay, so just leave that's an acceptable answer.
That's, I think, the only acceptable answer. Because we don't know what theta is.
Right.
And it says you can use physical constants, and g counts as a physical constant. All right. Notice, you guys, also, I remember one of the things my students did last year was they put 9.8 in instead of g. Don't do that unless you've got other numbers to deal with. Okay? Just leave the g as g. Okay? All right. Any problems with that one? Okay.
Wait, so like so any problem that says like leave it in terms of any physical constants, just leave it as g?
Yep.
Cool.
Yeah, and then if eventually it gives you other numbers and you need to evaluate it, then you can go ahead and put in your 9.8.
Great.
Cool. All right. So let's see. Roman numeral 2 wants to know an expression for the velocity of the block at time t. Okay. Well, this one should be kind of a one-step thing. So you don't even need to do calculus. It's easier than that. Maggie, you got an idea?
G sine theta t minus v naught.
Yeah, look, it's this, you guys. So first of all, somebody convinced me that I can use this equation. Acceleration's constant, right? So v final means the velocity at the end of some time t. So my velocity at the end of time t is whatever my starting velocity was, that's negative v naught, plus, like Maggie said, the acceleration is g sine theta times t. There you go, there's your answer. Now, if you write g sine theta t minus v naught, great. You know, obviously you can rearrange this algebraically, but that's the answer. Cool? Any problems? Adam, you good? Talk to me. Because you walked in the door and you were like, wasn't that one really easy? And then I was like, I don't know, there were some common mistakes. Sounds like you fell into that camp. So talk to me.
So this equation, did it come from the acceleration is equal to velocity final minus velocity initial over time?
Yeah, this algebraically is the exact same as Vf minus Vi over T.
Oh, yeah. Okay. I think, yeah, I'm good.
You sure?
Yeah, I got it now. I just did something wrong.
Okay.
Yeah.
And you know what it was?
Yeah.
Okay. All right, is everybody good up for this? All right, Roman numeral 3 says, give me an expression for the position as a function of time. So once again, you can use calculus to solve this, but there's a much easier way to do it. It's the acceleration's constant, right? So we want to come up with an expression for displacement as a function of time, but we can only use our given information. So I guess you could use Vf, but then you'd have to substitute in this Vf equation, right? So the one that jumps out to me is, I wonder if we can use this equation. Do you guys see why I zeroed in on that equation? Yeah.
Since I never asked you to have it as a function of time, though, can you use like the 2a delta x is equal to Vf squared minus Vi squared?
It does, because the text in part A says, consider the motion of the block at some time t.
Okay, I see that. I got you.
So, yeah.
So just use a different equation.
Right. Yeah, I think that's the only way you could do it. Because any other equation, would, like the one you talked about, has Vf in it.
Yeah.
And that's not one of the given variables that you're allowed to use. So you then have to replace Vf with your answer from Roman numeral 2. Follow?
Yep.
All right, is everybody good? All right, so true or false? So here's my answer. 1/2 g sine theta t squared minus v naught times t. Is that my answer then? Because I just plugged in my numbers.
You're trying to trick us.
Delta people, it goes up and down.
Oh wait, no. Then for the D, you go. Yeah.
Okay, what do you got?
Wouldn't you have to add on the D because it's your initial position?
Good. So this is an expression for the change in position. This is xf minus xi equals that, right? And our xi is d. So you got to add d to both sides. So you get this. X final, that's our x at time t, is this mass 1/2 g sine theta t squared minus v naught t plus d. Yes.
Convince me why I shouldn't have taken the integral both times, because it worked.
Great. I just think calculus is harder than algebra, but
Oh, okay.
so no, I didn't mean that in a snarky way, but yeah, you can do it that way. Take an integral.
Alright.
But the advantage of those kinematics equations, like the 1/2 at squared,
Is that
it's done the calculus for you.
Yeah.
Do you know what I mean?
Yeah.
So you guys, anytime your acceleration is constant, my preference would be to have you not doing calc if you can avoid it. And so use those constant acceleration equations off of the sheet, you
You
know?
would never have it.
Carla, you good?
Yeah.
What's up?
Nothing, I was just thinking, if you wanted, you could make equations for position where acceleration was variable, because if you held jerk constant, then there
Totally.
would be like really complicated position equations with variable
100%.
acceleration.
Yeah. Yeah, and then there'd be a whole litany of those to solve for, right? Because you'd have an initial acceleration and a final acceleration, and it would get really ugly. All right. Yeah, Evan.
Why can't you just use delta x over t?
Why can't you do delta x over t? It's not. Delta x over t is the equation for average velocity. Delta v over t is acceleration.
Oh, but it's not average. That's the problem.
Right.
You can't. Beep, beep.
All right. Are we good? All right. So that was letter A. Does anybody have any questions about how we did part A? All right.
Derive.
Part B says derive an expression for the position x min of the block when it's closest to the motion sensor. And then it tells you what variables you're allowed to have in your answer. Notice, you can't use t anymore. Okay? So, there are a couple of ways of doing this. You can do it using conservation of energy, but it's not the way that I immediately thought of. So, we're trying to find... The idea is the block is going to go up the hill and come down, right? We know x is d here. We know x is 0 here. We want to find x at this point, right? So, what are some things we know about that point that might help us solve this thing? Sure, what do you got, Peter?
Velocity is 0.
Cool, the velocity is 0. Why would that be helpful? Why would knowing the velocity be helpful? Equations.
Yes.
A little more. That's funny. So a little more specific. Why does knowing that the velocity is 0 help me? I'm not trying to ignore you, Peter. I just want other people following along. All right, Donald, what do you got?
That I need to know that the GPE is at its max at that point.
Okay, so let me come back to that. So there is a way to do it using conservation of energy. And you're right. Your GPE is at its max. So you could solve... So if your GPE is at its max, what's your KE going to be? 0, right? So one way to do it is to solve for that height and then do a little bit of trig and it works. All right? There's another way of doing it.
That's how I would probably.
Okay, well, let's do it both ways and make sure we get the same answer. Sure. Okay. Maggie, what do you got?
Can you just use like a mathematics equation to do this?
Yeah.
Okay, so just like 2a delta x.
So 2a delta x equals vf squared minus vi squared. That's even easier than what I did.
Yay!
All right, because look. Let's see. No, this is good. So you're telling me we can find our delta x, right? So let's see. So 2a is g sine theta, right? Times delta x equals vf squared, which is 0, minus v naught squared. Well, minus negative v naught squared, right? Right? So delta x is going to be negative v naught squared over 2g sine theta. This is even better than what I did. All right, am I done?
No, that's D.
No, with the d, can't you make like x minus 2 or something for your delta x?
Yeah, totally, yeah. So remember, you guys, this is my delta x, right? So this is final position minus initial, which is d. So you guys are exactly right. Add your d onto both sides, and you're done.
So would a midterm act like usually like a little harder than that?
It would be this, but maybe with numbers.
Oh, okay.
Did I see it? Okay, so
I think this year I've erred on the side of not. Well, anyway, go ahead.
am I imagining things or did I just think it's going to disappear? Oh, wait, no, because the V naught is squared.
Yes.
No, I'm so
Clear?
confused. You're squared.
Yeah, we're good.
Carla, and then
Your
Kitty.
d naught is not squared then anymore.
Oh, the squared, that's my bad.
Okay.
A squared disappeared, that was my mistake. Patrick, what's up?
What did you do?
Sorry?
What did you do?
What do you mean, more specific?
You said like this was you did.
It's not an equation, right? What did you do?
Oh, I see. Sorry, I thought you meant what I do here. I was like, I gotcha. Okay, I gotcha. What I did was, and yes, this is way better than what I did. But what I did was earlier we found this equation to find our velocity at time t. I set that equal to 0 and solved for t. And then once I had that t, I plugged it into our position equation.
Nice, that's nice.
It wasn't too bad, but the algebra was harder than the Maggie's solution. So, all right, let's do it real quick using conservation of energy. The conservation of energy solution is not bad. All right, so Donald, I'm going to put you on point here. So here's what we know. Oh, that's a. All right. So help me out, Donald. So, because you were talking about conservation of energy, right?
Yeah.
Sorry, are you back on board or?
I'm a little bit out right now.
So you were saying that at the point where it hits its highest point, the GPE is at its max,
Yeah.
right? So kind of walk me through how I could use that to solve this problem.
Sorry, I forget what it was asking. I was just saying because you were saying at the point that it's 0.
Gotcha.
So I just was saying.
I gotcha. Okay. All right. So let's run through this, you guys. Look. So the idea is at this bottom point, I know my height is 0, right? And I know that my velocity is negative v0, right?
So we can say 1/2 mg squared, right?
And I know at the top, I know my velocity is 0.
Yeah.
And I know my height is, well, let's see. If I consider this delta x and I consider this h,
Oh my god.
then that ought to be delta x times sine of theta, right? Everybody okay here? All right, so somebody who's not passing a pizza box around, tell me something useful about the energy of those 2 points that I've got on the board up there.
They're equal. Total energy.
Total energy is equal. Cool. So let's break it down. Sure. Adam, what do you got?
At the top, kinetic energy is 0.
Okay, so at the top, the kinetic energy is 0. So at the top, what kind of energy have I got? Just gravitational potential energy, right? And at the bottom, right? Good?
Sorry. I'm really something else.
Everybody say thank you, Donald.
He wouldn't accept our message. Yeah.
All right,
That's why it's really.
let's finish this up, you guys.
That's why we are arguing.
Yeah, we do need to focus. I got stuff to do too. All right, so look. So at the top, all of our energy is GPE, right? So that's m times g times our height, which is delta x sine theta, right? Equals 1/2 m times v0 squared. So let's see. The m's cancel. If you solve for delta x, you get v0 squared over
It's like weirdly.
2g sine theta.
The negative.
And it's moving, the position's decreasing. So yeah, you'd have to sort of manufacture this negative sign, I guess. Yeah, that's the only way it works. And then add d and you're done.
Okay.
Cool?
Yes.
All right. Any other questions on that page? No. All right, last page, these graphs. I very much like this problem. Yes?
Maybe it's not negative because, or like it originally isn't negative because our the delta x that you were doing is like backwards.
Say that again?
Because technically delta x is negative, right?
Yeah.
So then when you put in mg delta x sine theta, delta x should have been negative. And since you didn't do that, that's why it wasn't negative.
Gotcha.
Doesn't that make sense?
Yeah.
Okay. Well, that's how I'm going to do it.
Yeah, I don't know that I love that. Oh, right. I see what you're saying. That yes, that if I put a negative in there, I agree with you. Because you're yes
is technically going backwards, so it's
right.
negative, so h is
I agree.
yes.
I agree. I got it now.
Sweet.
Cool. All right, you guys. Question C. On the axes provided, sketch graphs of position, velocity, and acceleration as a function of time. So, what is this? Question C?
Yes.
All right. So position versus time graph. What's the starting position, you guys? D. What should the graph look like?
Something that goes down to 0. Or no, just kidding.
No, it goes up first.
Kidding.
Does it go up or down?
It goes down.
Up and then down, right?
It goes down. It goes closer to 0.
Do you guys agree when you first push it, you're pushing it up the ramp closer to a position of 0, right?
Yes.
Notice it never dips to negative, right?
Right there.
Isn't this my x min,
That's D.
right?
Or that's X.
That's d, right? This is x min that we just found in part B, right? Follow? Everybody good?
Yeah.
All right. Velocity as a function of time. What does the velocity start at? Negative v naught. Then what does it do? Show me your hand. Goes up, right? Your acceleration's positive g sine theta. And it's constant. So that graph has to have a constant slope. And then your acceleration graph
Is another line.
is a line at g sine theta. That's the worst line anyone's ever drawn. It's supposed to be horizontal.
It's down.
All right, is everybody good up through C? All right. Yes, good? Yeah, okay. All right, D. All right, D. After the block slides down and leaves the bottom of the ramp, it slides on a horizontal surface with a coefficient of friction given by mu k. Derive an expression for the distance the block slides before stopping. So the idea is the block's going to get back to the bottom of the ramp and it's going to slide on a horizontal surface, right? So it goes up the ramp, slows down, stops, comes down the ramp, speeds up, and then hits this horizontal part. What's the velocity going to be when it gets to that horizontal part? Good, v naught, right? Because our path is symmetric, right? Everybody good? All right. And so what we want to find here in part D is an expression for how far it will slide before it stops. So, what should we do? Sure, get me started, Tebo.
Get some forces on that zone.
Get some forces on that. I love it. So talk to me. What do you got?
Friction.
I can't do friction yet. Well, I guess I can.
Normal force.
Everybody okay with why I put friction going this way?
Yes.
Kinetic, right? What else?
Gravity.
Gravity. I want you guys to always start with gravity.
Try my best.
And then you can put in normal force because you know the normal force has to be big enough to cancel out your gravity. Ouch.
And now we know friction.
And now we know this is our coefficient of static friction times normal force. Oh, kinetic, thank you. Thank you, thank you, thank you.
Why isn't that negative?
It is negative. Very good. Thank you, Carla.
You thought I was bad, and then Carla spoke up.
You can give them the finger if you want. That won't show up on the video. All right. Everybody good? All right. Cool. We got our forces. Now what?
Reference equation.
What do you got? Reference
No,
equation?
find acceleration based off that, and then reference equation.
What do you mean when you say reference equation? Is that a thing that I don't know?
Find one that you like and use it.
Oh, gotcha. Okay. Sure. So find the acceleration off that. So talk to me about how you're going to find the acceleration off that.
Well, there's only like one important force I care about right now. So that's just the mg UK thing.
Uh-huh.
So then negative that is your acceleration.
You're
no.
super warm. Yeah.
So Fn times that.
Right? Mass times acceleration equals negative mu k mg, right?
We should have that one.
Net force equals net
It
force.
should be tattooed with mass teachers not equal way.
All right, masses cancel, so now I know my acceleration.
Really? Because I thought math was weight. Are you sure, Carl? Because I'm not sure still.
Everybody good?
Anymore.
All right, so now I think we can probably use the Maggie equation.
This was my favorite equation.
All right, so here we go. Negative 2 mu k g delta x equals 0 minus v naught squared. And solve.
Oh god, that is not
Did I do that last part too fast, Subs?
If I use the 1/2 AAT squared plus VIT, it's probably equal to the same thing, but it looks totally different.
So the problem, though, is that you're not allowed to use t as one of your variables.
Yep.
So if you solve for t in terms of, you know, the displacement or whatever, or d, I guess. Oh, yeah. All right, are we good? Everybody good? Questions, problems, concerns? All right, last question. I really like question E. You really got to think about this one, even though there's no numbers. All right, E says, suppose the ramp now has friction. The same block is projected up, the same blah, 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 blah. And then it wants a velocity versus time graph. All right? So with no friction, our velocity time graph just looked like this, right? A nice straight line. With friction, that's going to change things, right? Thoughts about how? How does friction change this?
If they're like, okay, so there's friction, and everything in this question is variable, it's all exact numbers, how do you know it doesn't stop at the top?
Yeah, what's our time?
I think it says that in the text of the problem.
It says it doesn't stop at the top?
Comes back down the ramp.
And comes back down the ramp.
Oh, okay.
You're correct. You're correct. It's possible that with friction it might never come back down. But it tells you in the problem it does come back down.
Oh. Is that what you had to say, Pat? Because, okay, right. So when you're going up the ramp, your acceleration is constant. When you come back down, friction changes into the other direction, changing the acceleration. So
There are two distinct accelerations. As the block is going up, think about what forces are acting on it. As the block is going up the ramp, talk to me. What forces are going to affect the motion? Friction and FG parallel. Right? And then coming down the ramp, Adam hit the nail on the head. The friction changes directions. Look, my FG parallel is still the same, but now my FFK goes the other way. So where do I have the bigger net force? On the way up. So where do I have the bigger acceleration? On the way up, right? So my velocity begins at negative v naught, and eventually you slow down and stop. and then you come back down the ramp with a smaller acceleration, right?
Yeah.
And do you agree that it's going to take, what does it say? It says something about t final over 2. So the original ramp, oh, I see. So the total time is t final, right? So here's our t final, and then t final over 2. Does that make sense? In other words, it's going to take less time to go up than it will to come down, because on the way up there's a bigger acceleration because there are 2 forces impeding its motion, and on the way down there's only 1 force impeding its motion. Cool?
Yes.
Carly, you started to say something. You said, so we make like...
Yeah, we just, sorry, I didn't remember.
You sure?
Yeah, we just like randomly choose a point before T2.
Exactly, yeah. There's nothing magic about where I put that point as long as it's to the left of your pathfinder. Cool, you guys?
Yeah. This was fun.
Helpful?
Yeah.
Some?
Yeah.
Okay. All right. So, I think, as I said, I think before you came back into the room, I think number 2 is more similar to what you'll see on the midterm than number 1.
That was on you, man.
Yeah, guys, I really think if you go back and look at old tests, look at old homework assignments.
Great idea.
Sure.
Yeah.
Thank you.